The last thing we want to do as an introduction is to look at two case studies, one of them a long span and one of them a high rise. We'll talk in later classes about the precise definition of those terms, but basically two structures that are larger than what you would find in a typical daily practice, and how they both exemplify some of the principles that we've looked at, the 5 S's, but also how they recall some of the things that we looked at in the history lecture as well. And the two case studies are both from the kind of mid-20th century. One of them is an exhibition hall in Turin, Italy, by an Italian engineer and builder named Pierluigi Nervi. The other is a little closer to home, the John Hancock Tower on North Michigan Avenue in Chicago. The Nervi is concrete and long span, the Hancock is steel and high rise. And both of these really exemplify a principle that I'll come back to over and over that's called structural art, that takes the principles of structural engineering and isn't really happy with just solving the problem, but really wants to turn those into something that is more sculptural, more evocative, more artistic, without getting too far away from the principles that drove it. Both of these buildings are kind of internationally known. They both won all kinds of awards for their architecture, but they're also really good examples of engineering, really efficient engineering, and particularly in the case of the Exposition Hall in Turin, a really great example of particularly clever construction, something that we know we have to do, right? We have to go out and build these things, but how you build a 200-foot span concrete building given relatively limited resources, as we'll see, is a little bit of a trick. And construction, of course, always plays into how structures end up functioning. So to start with, the Exposition Hall was built between 1947 and 1949. And if you know your history, of course, that's a really fraught time in Italy because the country is recovering from World War II. And Turin, which had been the automotive capital of Europe, where Fiat made all of its cars, was basically in ruins. The commission was to build a new exposition hall that would be ready in time for a large international auto fair in 1949. And the companies sponsoring this went to contractors and said, you have 18 months, start to finish, to build this. Now, Italy in 1947 is kind of bereft of resources, right? It's hard to get things anywhere because they're rebuilding the whole country. And Nervi, who is trained not only as an engineer but also as a contractor, and who by that point has been building concrete structures for about 20 years, puts together a proposal that says he can not only do it on time, but he can do it without renting a really large crane or any really huge equipment, which was in short supply at the time. Now, how could he do this? Well, he had been commissioned by the Italian Air Force in the early years of World War II to design and build hangars for the Italian Air Force, for their airplanes. The country had no access to steel. Italy doesn't have a native steel industry. And because of embargoes that had been happening since the 1920s against the Italian regime, they couldn't import large quantities of steel either. And Nervi solved the problem of how you make long span hangars in a country with no steel by turning to concrete, and in particular a variant called Precast Concrete, where you make the elements of the structure on the ground in little molds, and you basically glue them together on the site. And here you see his early experiments in precast concrete construction, trying to think about how you would build a long span arch out of lots of little pieces. And the key to this was using what little steel he could get to make very heavily reinforced joints between all of these elements, and then designing the elements in a way that took advantage of precasting, that let him make fairly complicated shapes in concrete that took out these huge areas of material. And when we get into beam design, we'll talk about where those holes are along that arch and why it makes sense to remove what we call dead weight, or material that's not working as hard as it might be, from the center of beams. Now, looking at this, you might say, well, that looks like an arch. And it is an arch, but it's a very specific variant of an arch called a beam arch. It's a very shallow arch, and it works a little bit like an arch that the Romans would have built, or that Gustav Eiffel would have built in one of his railway bridges. But it's too shallow to work only like an arch. And it also works a little bit like a curved beam. It goes into bending. And you might remember we talked about the ideal shape for a beam being an I-beam, right? You see that on steel construction sites all the time. This is a variant of the same principle, where you try to put most of the material at the far edges of a beam, the top and bottom, what we call flanges of an I-beam, in this case the top and bottom of the arches. And Nervi's able to do that because he's casting all of these pieces on the ground or in a workshop, bringing them to the site, lifting them up, and sort of gluing them together. Now, he also had done some work for the Italian Navy in the middle of World War II. A country without steel has trouble building ships, and the Italian Navy went to him and asked if he could experiment with concrete boat hulls. Now, this sounds counterintuitive. Concrete strikes us as heavy and dense and something that's likely to sink, but Nervi experimented with a particular type of concrete called ferrocement that uses small quantities of metal wire. It was possible to get some metal, some steel, but not a lot. He embedded this metal wire, this metal mesh, into very, very thin layers of lightweight concrete, right, without all the kind of gravel and pebble and stuff that we're used to seeing. With this, he was able to make very, very thin shapes, and he was also able to make curved shapes very easily. He could bend the wire into the shapes that the hulls had to be. He could get some laborers to just trowel the lightweight cement into it, and he created these hulls that were ultimately successful. By 1943, Italy was kind of retreating up the peninsula as the Allies were making gains in World War II. They never built more than a handful of these. But Nervi remembered this, right? Because a structural engineer is not only trying to span great distances, they're also trying always to save weight. If you can make a lighter version of your structure, then the structure itself has to do less work, the foundations have to do less work, you start saving money in exponential ways. And what Nervi realized was that he could combine precasting with ferrocement to basically break large, long-span structures down into small, very, very lightweight modules that could be handled by crews of just 3 or 4 workers instead of very, very large tower cranes. And so when he comes to the problem of the Turin Exposition Hall, what he decides to do is to break that huge span down into hundreds and hundreds of little tiny ferrocement boats, for lack of a better word. He hires a bunch of workmen to take metal mesh, to bend it over forms, to trowel cement into it, and to let those cure, to create hundreds and hundreds of these little kind of boats, almost like canoes. And you can see that there's a little bit of a curve to them. There's a space here that's going to be a window that separates the top and bottom. These are the pieces that are going to end up doing the work. And it has these planes, these sort of triangles on the edges called diaphragms that are going to both stiffen the little boat and also allow him to basically glue that boat to another boat right next to it. Right? So he's going to literally break this big span down into hundreds and hundreds of little pieces and literally glue all those pieces together on the job site. On the left here you can see workers building one of the boats. This is the metal mesh in the little reinforcing bar cage. This is the mold that they're bending it around. And here's the actual job site yard. And you can see that they are just making hundreds of these. They're all about 9 or 10 feet long, and they all weigh about 200 or 300 pounds. So a small group of laborers can move them around relatively easily. And they're building this while all the foundation work is going on. So they've found a way to save months and months of time fabricating all of these by basically telescoping the schedule with the foundations. When everything is ready, they take each boat in turn and they lift it up using a winch and 2 or 3 men pulling on a rope. So they don't need a crane, they just need a pulley. They put that onto a little rail and slide it down until they can glue it onto the little hull or the little boat that went right before it. And you can see what's happening here. There's a very, very lightweight scaffold, and that makes the shape of the arch. It's a circular arc, not a great shape for an arch, but a great shape for a beam arch. And each one of these little ribs is going to function like a combination of an arch and a beam. If you look really closely, you can see a couple of things going on. One, just like Nervi's early experiment, he's taken out dead weight in the middle of the beam arch, right? Fundamental beam principle. He's shaped it according to a long, sort of shallow curve. Not great for an arch, but better than just a flat beam. And if you look really, really closely, you can see something really interesting, which is that these ribs go from a relatively shallow depth here to a relatively deep depth here. And you might remember the gate at Mycenae, the lion gate, the stone lintel that we saw over the doorway from about 2500 BC, where intuitively those builders knew that a beam wants to be deeper in the middle, shallower at the ends. And Nervi's using exactly the same principle here. The other thing you might notice is that when these are all glued together, he has this sort of sequence of ribs, this kind of what we call a folded plate. So even though each one of these little boat hulls is only about 2 inches thick, the beam arch here thinks that it's a couple of feet deep, right? It works like a beam that's much, much deeper than it actually is, right? Than the actual thickness is. So he's saving weight by making this corrugated folded arch, right? Taking out a lot of weight that you would have if this was a solid rib. He's saving weight by taking material out along the neutral axis, just like a steel beam. And he's also saving weight by tuning the shape of the arch to how he knows it wants to perform, right? Narrow at the ends, thick in the middle, where the greatest bending stresses are going to be. And here's the result. Now, he's very, very clever in how he kind of takes all of these loads, all of these weights, and sort of channels them into these buttresses that are along the side of the hall. Those are exactly like the flying buttresses in a Gothic cathedral. They take the loads from the ribs, they collect them, and they channel them down into the foundations. You can see that they're at an angle, just like flying buttresses in a Gothic cathedral. And that's because an arch or a beam arch, when you push down on it, the base of the arch wants to spread out, right? It wants to what we call thrust, and that's the way that arches want to fail. They want to translate the vertical loads that they're experiencing under gravity into horizontal thrusts and flatten out and fail that way. And you can see that these buttresses are leaning in to the arches, taking the thrust at an angle down into the foundations. Now, Nervi's not trained as an architect, but he makes a few little detailed decisions that turn this from a very, very practical, very efficient way of solving the problem into something that's really poetic. One of them is the way that the buttresses and the ribs are attached. You can see these little fan vaults along the side that not only collect those loads, but make it very visible how those loads flow down into the buttresses. The other thing that I think he does that's really interesting is he exposes those diaphragm walls, right? The ends of each of those little ferro-cement boats are visible, and they actually modulate the ceiling. They give it a pattern, they give it a kind of rhythm. They break this huge scale, this huge span, down into something that's much more humane. Remember that each one of these was lifted by 3 guys and a pulley. And so this is very much a kind of human scale being imprinted onto this very, very large scale. And it comes out of not only the kind of grammar or the language of structure, but also the grammar or the language of construction, how you break a big thing down into little pieces and bring them to the site. A lot going on here, not only to solve the structural problem, but again to turn it into an example of structural art, something that is not only efficient, but also arguably quite architecturally beautiful. So our other case study does the exact opposite. Instead of spanning a great distance horizontally, it spans a great distance vertically. The Hancock Tower in Chicago is one of the tallest buildings in the world when it opened up in the late 1960s. Now it's not even in the top 30 or 40, but it still stands as a great example of how a skyscraper can do some of the same things that Nervi Exposition Hall roof does, namely take a really big, really impressive structural achievement and give it a scale that's kind of human, right? Break it down into something that feels a lot friendlier and that communicates something not only about how it works, but also how it was put together. The Hancock has a really interesting history. There was an original scheme in the early 60s for just a residential tower that was going to be 65 stories tall, and they were struggling with how to take a great big floor plate and turn it into kind of usable apartments. In apartments, what sells really well are windows. You have to get a certain amount of floor area for a 1-bedroom or a 2-bedroom or a 3-bedroom, but what gives the apartments real value is views, the ability to see out. And so this initial scheme by developers called Mack and Schur and an architect named Al Shaw was trying to get as much window space and area as they could. And as you can see, they weren't able to use much of the site. They used a fairly standard apartment plan, and what they ended up doing was basically wasting volume all around it. Right? They could have built much, much more. They were stuck, though, because they were trying to get more perimeter into the scheme than they were actual floor area. That scheme kind of died, maybe deservedly, and instead, after a few years, another developer came along and hired SOM, a well-known Chicago commercial real estate firm by that point, to do a scheme in about 1963. And the two principals who worked on it, Bruce Graham was the architect, Fosler Khan was the engineer. They had already developed a reputation for combining, for integrating architecture and engineering. Graham really appreciated the kind of structural language that Khan was able to come up with. Khan understood that he had to do more than just solve the problem, that they wanted to solve the problem really elegantly. In 1963, they did a scheme that included about 50% commercial office space and 50% apartment, residential space. And the traditional way to do this was to build two separate towers, take the piece of land and build one commercial office building and one residential building. And the reason for that is that commercial office buildings have to be quite different than apartment buildings. In commercial office buildings, you really are selling the square footage. Views are much less important. They're nice, they maybe increase rent a little bit, but nowhere near as much as in residential construction. So in offices, it's more efficient to build deep floor plates, 35, 40, 50 feet from the elevator core to the perimeter of the building or the skin. And typically, we have much higher floor-to-floor heights because we have to get a lot more mechanical service in to make the office work. So standard at the time was about 14 feet from one floor to the next. So in the apartment tower, shallow floor plates, a much lower floor-to-floor height, air conditioning usually done with window units or fan coil units at the perimeter instead of through lots of ducts. So they had these two programs that had very, very different requirements. And for the initial phase of the project, they just did a very traditional two-tower scheme. They weren't real happy with this, though, because this site on North Michigan Avenue had lake views in two directions, and they realized that no matter what they did, they would be blocking some views of one building or another, however they put them on the site. And the story is that Khan one day literally took the apartment tower model and glued it on top of the commercial office tower and said, look, if you do this, if you literally put the tower with the shorter floor plates, the shallower floor plates on top of the deeper floor plates, you will not only solve all the problems, right, but you'll get this really, really tall, 1,000-foot tall building that'll be a real landmark. And what they ended up realizing was that if you created this kind of sloped profile to the building, you would get apartments down here that were maybe a little bit too deep, offices here that were maybe a little bit too shallow, but still workable. And that you could actually tune the shape of the building to the program that was required. And if you did that, you would get a very, very good structural shape, one that's wider at the base and skinnier at the top. The principles that they ended up working with structurally were, first of all, that principle of a wide base, right? Spreading your feet out when you're standing in a windstorm, giving yourself more footprint, or what a structural engineer would say, more resisting moments at the bottom by giving yourself greater leverage down here. Eiffel Tower is the perfect example of this. It's designed primarily against wind forces. The tower itself weighs practically nothing because it's mostly air. What Eiffel was worried about was the wind knocking the tower over, and so the feet of the Eiffel Tower are spread far apart, as are the feet of the Hancock building, right, following the deeper floor plate program of the offices. The other principle is the truss, or triangulation, and we've seen this as far back as the pyramids, that a triangle is the ultimate structural shape. And it's the ultimate structural shape because when you put three fixed legs together, there is only one triangle that they can form. If you put four sticks together, they can form a parallelogram, they can form a rectangle, they can form all kinds of different shapes. It's a flimsy shape. To bend a triangle, right, or to change the shape of a triangle, you have to break or stretch or squish one of the shapes. You have to actually deform one of the structural elements. And a truss takes advantage of this by taking the rectangles that architects need to design to, right? Our clients want square space or rectangular space, not triangular space. But by adding elements, cross elements to those cubical bays, what you get is a triangulated system, and therefore a system that's much more rigid than if you just had squares or rectangles. The truss principle, or the cross-bracing principle, you can see it here in Eiffel's Tower. This is the sort of second piece of the Hancock secret. As a result, once Kahn came up with this sort of idea of a giant set of trusses going up the outside of the building, tuned to the deeper floor plates down at the base, the skinnier floor plates up at the top where the apartments were, what they realized was that this truss would not only take all of the wind load, but the Hancock would function as a kind of giant column. All of the structure on the outside is, for reasons that we'll get into in a later class, the ideal arrangement for a column, something that a linear element that's carrying weight axially along its length. And all of that truss work meant that a load anywhere in the building would eventually get distributed throughout the framework below, that these cross braces not only hold the building up against wind, they also help to distribute the load through the framework below. And as a result, the Hancock was, per square foot, the lightest office building ever built. We buy steel by the pound, so if you're building a much, much lighter structure, you are saving money on steel. You're also saving money on foundations because you're putting less load into the soil. You can understand the Hancock mathematically, right? These are some of the engineering drawings as presented by an engineer who worked for Kahn named Hal Iyengar. And you can see that there is an awful lot of math going on. What's happening is that all of these members in the Hancock are pushing or pulling. They're undergoing a stress, either tension or compression, in a way that makes the whole structure stay in equilibrium, right? It prevents the building from moving. And we can go in and we can actually figure out, using a little logic and some trigonometry, how loads get distributed through that entire framework. It is a long, exhaustive, tiring process, but we can also just look at the Hancock and we can see that it's a strong scheme. We may not understand every nuance of the mathematics that makes it work, but we look at the shape, the spread footprint at the base, narrowing, tapering as it goes up. We recognize that naturally as an efficient wind shape. If you think about it, it's kind of a cantilever beam that's sticking up from the ground instead of sticking out from the side of a tree. That big base of the Hancock is like the deep root of the good tree branch that we want to grab onto. And looking at the cross bracing, we intuitively understand that triangles are strong. And we can think of that, even if we don't understand the math, we can think of that as a kind of network for distributing both the weight of the building across the foundation and also what we call the lateral loads, wind loads that are hitting the side of the building, taking those down into the ground as well. In addition to being a great engineering solution, the Hancock, of course, is iconic. It's one of everyone's favorite buildings in Chicago. And I would argue that the reason is that these cross braces and the general shape of the building are structural ideas that we can intuit. You do not need 5 semesters of SciTech to look at the Hancock and feel like that is a strong solution, an efficient solution. I think that's one of the reasons that the Hancock is such a popular building, right? Often more popular than the Sears Tower, which is just down the street and is something like 200 feet, 200 or 300 feet taller. The Hancock speaks to us, right? Its exterior is an expression of the structural principles at work. We appreciate that, right? That to me is an example of what we call structural art. Interestingly enough, one of the things they were worried about when they were designing the Hancock, the developer was worried about whether all of these cross braces would actually decrease the property values inside. And in fact, those diagonals are such a signature of the building that the rumor is, not sure how true this is, but the rumor is that if your apartment has a diagonal cutting across the window, that actually increases the value, right? It's seen as a kind of feature or a piece of the building's signature. There are interesting things going on, like a 2-story gap where the building switches from office to apartment. And to change the kind of rhythm of the floor plates, to go from 14 feet to 10 feet and have the diagonals all work out, there is this double-story kind of adjustment space. And into that, the developers have thrown what was billed at one point as the world's tallest swimming pool, right, up about 600 feet in the air. But you can see that the expression of the building, even when you don't have diagonals, is very much about the kind of cage of steel columns that wrap around the building. And the only real failure of the Hancock, of this brilliant engineering solution, occurs at the 95th floor. There is a fancy restaurant called the 95th that is on one of the very, very top floors. And you can see here, this is the last of the diagonal cross braces. Great view out over Lake Michigan. The building was so light that in a windstorm, what they discovered was that it moved around well within what they expected. It moves about 8 to 10 inches very, very slowly in a windstorm, so you can't really feel it. If you are standing very still and sort of looking at the horizon, you can tell that you're moving a little bit, but that's not really unusual for a skyscraper that tall. What is unusual is that there is a restaurant on top and a wine cellar in that restaurant. And the constant motion of the skyscraper actually caused the wine, the solids in the wine to settle in ways that, in really great vintage bottled wine, apparently changed the way it tastes or changed the flavor. This was a failure really more of putting a fine dining establishment up so high in the air than anything structural. But I think it talks about just how incredible the Hancock is, that it's so lightweight that it actually moves around enough to spoil a bottle of wine 95 floors up. But the real impact, I think, again, is that Kahn and Graham, the architect and engineer of the building, understood this dialogue, understood that structural principles like cross-bracing or a wide footprint or regular column bays, right, regularly sized column bays, all of these things are not only good engineering practice, they are also things that explain to us or express to us something about how the building works. And we as human beings like that. We like to understand our environment. We like to know what we're getting into when we walk into a building. The cross-bracing is a kind of intuitive wind bracing technique. You can see too that it breaks the scale of the elevation down, so we don't just go from 1,000 feet down to like the 14-foot floor-to-floor height. We have this kind of intermediate scale that helps our eyeballs adjust and sort of grasp the great big scale of the thing by sort of mediating between that small window scale and the big building scale, a lot like the individual modules in the Nervi building. There are also some nice ornamental techniques. You can see that Graham decided to sort of stick these little ridges, little aluminum I-beams on the outside to give the building essentially racing stripes, to emphasize its verticality, to make it seem just a little bit taller, a little bit more graceful than it even is. And that kind of ornamentation, decoration if you want to call it, I think is also critical, right? That it helps to key into our sense of really big things, how really big things work, and how they can actually be sort of stretched out and be proportionally much more graceful than just a simply solved kind of engineering problem. Okay, we'll leave it there. I'll leave you with these two quotes, one from a Princeton historian of engineering named David Billington, who coined this phrase structural art. And he said that structural art is this uncompromising search for efficiency, lightweight, speedy construction, long spans, tall buildings, which, in the hands of a master builder, expresses the humanizing potential of modern technology, right? I think that's a wonderful phrase, that these are not just technological objects. They're also cultural objects. They're objects that people spend time in, that they see in their cityscape. And we want them to respond not just to the financial and structural necessities that we know about. We want them also to be beautiful things. And fluently understanding structural principles is one way to do that. Kahn, talking about the Hancock about 15 years after it was finished, he said that it's based in reason and the laws of nature, right? Laws of physics are totally in evidence there. But the aesthetics of the building, he said, have this value that goes beyond just the basic principles, and also beyond the kind of arbitrary forms that he said in 1983 reflect the fashion of the time. He was writing then in the midst of postmodernism. I would argue that we have the same issues today about architects and cool forms versus forms that are more timeless, that have stood for decades and still sort of have some validity. You can agree or disagree. I'm going to argue that one of the real purposes of what we'll do over the next 4 weeks in 345, but also over the next few semesters in the entire structural sequence, is not only give you the kind of basics of structural engineering, let you know what to expect when you're working with a structural engineer, help you to make good structural decisions when you're working on your own designs, but also, again, like I said in the history lecture, to give you a sense of the kind of grammar or language that's underlaid a lot of architectural design going back 3,500 years. We'll dive in next week's lectures into some principles about forces and loads, what the difference between those are, how we think about them not only architecturally but also mathematically, and how we can use those to kind of break into structures and start to understand what they have to do and how they have to work to handle the loads that we want to put on them.